Welcome to the LPI virtual seminar this week. Our guest this week is Dr. Carolyn H. van der Bogert of the University of Münster. Carolyn got her PhD at Brown University in 2004, and since 2009 has been a research scientist at the Geological Planetary Institute for Planetology at WWU Münster. Today she'll be giving us a talk on the excuse me, I forgot to mention also a co-investigator on the NASA Lunar Reconnaissance Orbiter, which she's been working on in various roles since 2009 as well. So she'll be giving a talk on the deep time on the moon, the development and application of the Lunar Cratering Chronology. During the talk, please leave your microphones muted. If you have a question for Dr. van der Bogert, please type it into the chat and I will read that off at the question time at the end of the talk. Alternately, if you'd like to ask a question, please put that directly. You can put that in the chat and I will ask you to unmute your mic and ask that. With that, thank you very much for coming and please take it away.
Okay. So, hello everybody from like 10 o'clock in Münster in Germany, where it's just as hot here as in Houston today, although we've got the worst of it behind us. So today, it's good to see some familiar names in the participant list, as well as some new names, which I hopefully will meet you in person in the future. Today I wanted to talk about the development and the application of the Lunar Cratering Chronology, and it's going here. I guess I have to advance it. Arrows here. Okay. So the first, just as a basic framework to give you an idea of what kinds of background information we're going to be talking about today. These are the tools that that basically I use and that our group uses on a daily basis to develop a geologic framework for the moon. And these include remote sensing data from all different kinds of missions, all the way from Lunar Orbiter. We do a lot of surface mapping, which involves looking at morphological features and defining morphological units to build the relative stratigraphy of geologic units on the moon, also looking at the compositional information. And then where we're going to really put focus today is a correlation of surface mapping and surface units to the returned samples and hopefully sometime in situ measurements of radiometric ages. And that's our focus for today, because the timescales that we're going to get out of this tool are going to allow us to interpret not only the geologic history and evolution of the moon, but also feed forward to looking at other planets, and the Earth included. So I just wanted to show, I noticed that our student Wajia has joined us today too. Wajia did this really nice painting on 4 canvases to represent the lunar chronology, or how the telling of time using craters and using different data sets. And so it'll kind of, I'll bring it up again and again as we go through the presentation today. So we want to have a look at crater frequency. Or did I just skip one? Yeah, okay, I skipped one. The outlook for the seminar, just so that you have a map of where we're going today, is that we're going to look inside the black box that is the Lunar Cratering Chronology, so that everybody can be reviewed who maybe has forgotten some details about how it works. And if you don't know anything about it, I wanted to give you some details for how it works. And then I want to highlight selected efforts recently to update and improve the chronology. Then we're going to discuss its application. How do you actually use it as a tool to then get ages for surfaces that don't have samples? And I'll outline potential sources of error. Depending on time, I may be able to go into a little more detail, or if we run out of time, then I'll have to come back and do another seminar. And then finally, to give you the big picture, I want to assemble the global view of the absolute model ages that have been measured in the last 20 to 30 years, and basically have a look at what is deep time on the moon. Now, I selected deep time as a term for today because John McPhee, in his book, Basin and Range, which I highly recommend if you haven't read it, described the vastness of terrestrial geologic time as deep time, because billions of years is a scale that is simply incomprehensible to us as humans. And so he tried to put deep time in the Earth into kind of a better, like a framework where basically the appearance of man is just the very little tiny bit of a fingernail that would get filed off of the king's hand if he represented geologic time, for example. So we're going to try to get our heads around deep time on the moon and see how this gets us to a deeper understanding of lunar geologic history and feed forward to the solar system. Okay, so the first thing that I wanted to do is to take a look at the Lunar Cratering Chronology. And it's based on the idea that, the observation that the number of superposed impact craters on a given surface of a geologic unit, you want to have a specific defined unit, is directly related to geologic time. So this assumes, and it's empirically observed, that over time you accumulate more craters on surfaces. So if you translate this into having measured the diameters of all of the craters within a certain area that you're interested in, then we can transition to looking at a data representation of crater frequency as a clock. And basically what happens here, you've got your crater diameter in the x-axis and the cumulative crater frequency in your y-axis. So here you're adding up all the craters that you've measured in these particular size bins. The data is traditionally binned. It was originally binned as a way to basically save computational time. And now there are updates to the way that you can use, I mean, obviously we have computers at this point that we can use to calculate these things without binning if necessary. So anyway, so you plot these things. This is just one of the standard ways of plotting it cumulatively. And what you end up with the example here for crater size frequency distributions that are measured at different Apollo landing sites by Neumann et al. In 1975, you get these distributions of craters that basically are pretty parallel to each other. And what you can see then in a graphical representation rather than sort of the visual representation that we saw in the previous slide is that the older units are plotting higher in the plot and the younger units are plotting lower in the plot. Okay, so that gives us an idea of the relative ages of these geologic units. So for example, the Apollo 14 unit here, that material is older than the Apollo 14, the pre-existing craters eliminated. So there's like a younger surface there, or it's also younger, the Apollo 14 is older than the craters that were measured at the Apollo 12 landing site. Okay, so this is really cool because we can get relative ages between different locations on the moon, but maybe it would be easier if we could represent it with a single number or a single value rather than having to show these plots to each other all the time. So in the process of kind of selecting a standard way to represent this, one of the things that you could do is use what's called the N of 1. And this is the cumulative number of craters that are greater than or equal to 1 kilometer in diameter. So that's would be this number here. Okay, that would be the N of 1 for this distribution here. Okay, so but you can see immediately that some of the distributions don't have a measured crater bin that's at 1 kilometer in diameter. So how can we normalize these so that we can get an N of 1 value for all of these different locations so that we can compare them more easily? And this is where the standardization and normalization comes in with using a standard, what's called the Lunar Standard Crater Distribution or a production function. Okay, and so this is basically developed by, and I'm sorry this is so tiny, this is a really tall graph, but what's important is not to be able to read the little stuff here, but to see that we have really a large range of crater diameters represented along a curve. Okay, how did we get this curve? Basically, Neukom and his group counted or measured the size frequency distribution on very old surfaces that have very large craters, and then incrementally, piecewise, worked down to younger areas that have a lot of smaller craters. Okay, now the requirement for each of these sort of standard pieces is that those locations are single geological horizons, like a stratigraphic horizon, for example, Oriental ejecta, or a particular Mare unit. And they had to be areas that were not affected by a lot of secondary cratering or by later geological processes, because these are basically kind of the stratigraphic horizons that are representative of the moon. Okay, and so then these pieces, though, just like the previous diagram, here I'll go back here, are not aligned with each other. So there's a normalization process that happens where these distributions are all lined up with one another to form this shape. Okay, and so this is the standard crater size frequency distribution, or the production function. Now, it does represent, it gives you information about, for example, the size frequency distribution of the impactors that are hitting the moon. And it's implicit to this normalization that that shape of the impactor population has not changed with time. Okay, so this is an important point that we unfortunately don't have time to get into why it's so important today, but it bears on whether there were a change in population of impactors early in the lunar history or not. Okay, so that's a little teaser for if you want to go read more about that, or you can send me an email and I'll provide some information. So for this production function, now we have an empirical measurement that then can be fit with a mathematical function. Okay, and this was done in many different ways. There were the possibility of fitting it with power laws on the different branches, because you notice that there's slightly different slopes in different parts of it. And Neukom decided in the end here to do a polynomial fit so that he has one function rather than having it piecemeal. Okay, so then you have this function. You can use that then to fit your CSFD that you've measured and calculate your N of 1 value so that you can compare your ages of your units more easily with each other. Okay, so we've got those parts now, and we've got relative ages. We've got this N of 1 value that we can compare amongst themselves, but how can we generate an absolute age? This was the goal of the cratering chronology. And this is where the moon is really a unique case currently. I hope that won't always be the case, because we have samples from known locations on the moon. And so what this means is that the samples have been analyzed in the lab, and we have radiometric and in some cases exposure ages of the samples that we can say are related to particular geologic units at the landing site. So we can measure the crater size frequency distribution at the landing site and calibrate this with the radiometric age of the rocks collected there. Okay, so if you do this for all the landing sites, you can find this in Striffler and Ryder, because I know, again, it's kind of small and you might want to spend some time having a look at it. Basically, this is all of the age data that had been compiled up to that point for the samples from the Apollo and Luna landing sites, and then compared with the N=1 values for those landing sites. Okay, so now we have a distribution of data, and we can fit maybe a line to it. I wanted to show this figure from Neumann et al. 1975 because it kind of shows the thought process that was going on in trying to fit this data set. You can see that he was thinking, okay, the crater frequency here is constant, a time constant influx of impactors. Here, yeah, okay, it's a steep decline. What happens in the middle? Okay, this is obviously a really important question mark here, and hopefully will be partially, if not completely, solved by Changi 5 samples. And I'll say a little bit more about that in a few minutes. Okay, so flipping the axis around, because now we generally go from the older to the younger ages when we show the absolute chronology, the crater chronology. You can see actually that there are quite a few people that have tried their hand at fitting the crater calibration to the radiometric and exposure age calibration. And some are a little bit higher in the middle here, some are lower, some are steeper at the old end, some are more shallow, okay, and then we have the very young craters here, Tycho, North Wray, and Cone. Okay, so we can fit that then also mathematically, and then we have a tool that we can use to solve for absolute model ages, which I will detail in just a few minutes. So the other interesting thing is that we have a chronology function, or a set of different possible chronology functions for the moon. The moon is the only body that currently has samples of known provenance. And so then that kind of forces us to be creative and make modifications to the lunar chronology to apply to other terrestrial planetary bodies. And so here I show an example of how to make the conversion from the moon to Mars. Basically, so here is moon here in the solid line. And then Mars basically has, you want to shift the, you have to shift the curve up because of the greater number of impactors at Mars, but then you shift it over to the left because the impact velocity is lower and the gravity is higher on Mars. And so you can basically do this same kind of modification to the lunar chronology function for many other asteroids and planets. Okay, and so that's the way that you would take the lunar chronology function to then apply to other bodies. But you can also take a impactor size frequency distribution model and apply that instead to make a production function. I'll say a little bit more in detail about that in a minute. Okay, and so basically what we're left with then for beyond the moon is that we would really like to have samples from known provenance for other planetary bodies so that maybe they can have their own lunar cratering chronology calibrated for their own body. In the meantime, we can improve and add additional samples to the lunar cratering chronology so that when you feed it forward to the other planets that there's hopefully less room for error. Okay, so that was kind of the quick overview of the details of how the lunar cratering chronology was assembled and the development of the production function and the chronology function. And more recently, there's been work done on these individual parts. And so I wanted to highlight a few of those things. There's ways to update the standard distribution. And one example is a student of ours in Münster who is working on her PhD to basically review and update the lunar standard distribution that's empirically derived. And so she's working on trying to find the original regions that were used in the Neuquén work to check, you know, how they are doing in terms of like appearance in new lunar data sets and whether those need to be revised and updated. And at the same time, using new techniques to find areas that Neuquén's group may not have realized actually would be better representative of certain parts of the production function. So she's working on looking at areas where she can get a good distribution of the large craters and then working down to smaller and smaller craters. The other thing is that the Neuquén standard distribution only goes down to about 10 meters diameter in craters size. And now we have higher resolution data, not only from LROC, but the Chinese mission and also the Kaguya mission have higher resolution so that we can actually measure craters that are smaller than 10 meters. And so the hope is that then we could extend the production function to smaller diameters. Now, I also mentioned that rather than just using a empirical measurement of the production function, you can also substitute the standard distribution or production function with a production function that's calculated from modeled impactor CSFDs. And the big example here is McPhee's work in 2009. And basically you can take the observed size frequency distribution of different asteroid populations and then extrapolate that to smaller sizes and use that to calculate what the production function should be on the moon. And there are, you know, relatively, here the McPhee one, for example, is probably the green one to look at the best, compared with the red and the black lines for Neuquén's. You can see that they're similar, although there are some places where they deviate from each other. And McPhee also has the ability to add information about the target properties of the planet so that, because the target properties would affect the sizes of the craters that are produced. And so this kind of brings up one of the first big caveats that always needs to be paid attention to, is that all the n(1) values that we generate from using a production function, they shouldn't be casually compared with each other. You want to make sure that you're comparing n(1) values from the same production function. And it's because here you're going to be basically deriving a different number for the McPhee production function than you are for the Neuquén production function. And if you're comparing those to each other, you don't have a valid, you know, ground for then whatever it is that answer that you want to have. Like, say you want to talk about if a particular unit is older than the other one. So always make sure that your PFs are the same when you're talking about n(1)s. Okay, so not only could we update the production function, but we can also update the crater calibration. So this is where you basically would choose new reference locations. And this is with the new data sets that we have. Neuquén used a lot of lunar orbiter data and Apollometric camera data. And so now we have many new data sets. One example of updating the crater calibration is the Robbins 2014 work, where he looked at the different Apollo landing sites and selected areas around them and counted the craters anew. And Wajia, who's on the meeting today, so that's great. If there are questions later on, specifically about this work, you can ask her directly. She has been, for her PhD, systematically making new geologic maps of all of the Apollo landing sites with the goal of testing and improving the crater count calibration areas. And then she combines that with reviewing and integrating any new, more recent sample age determinations. And so her approach here, for example, is this is the same Neuquén count area that was used in the example that I showed earlier for talking about assembling the cratering chronology. She then recounted that on WAC data. And what you can see based on her geologic map is that actually there are two different Mara units within this overall area. This was something that Neuquén's group couldn't see because they didn't have the spectral data that we have today. So what Wajia did then was to select areas that were just on these two different Mara units to make sure, here is the landing site, that the crater size frequency distribution that's measured and will represent the Apollo 12 samples comes exactly from the unit that sample is taken from. So this is a slight difference here. Wajia focuses down on very specific geologic unit, very close to the landing site, and this contrasts to Stuart's work, where he took larger areas in the region to produce his chronology, his update for the crater calibration. So here, again, one of the very important things that I want to note here is that the N of 1 values that are measured here have to be measured in the geologic unit that's associated with the return samples. And this is not necessarily an easy thing to figure out. It takes a lot of work looking through the sample information and then the time to produce a good geologic map. Okay, so here, just to continue the example from Wajia's work, are her new fitted N of 1 values. And then she takes those values and can feed them into the Lunar Cratering Chronology. So here you can see in the bright red color her two new points that she checked, and they plot actually right on the Neuquén chronology curve. And so at this point, Wajia hasn't fit a new chronology function to her data because we're basically, with Apollo 12 here as the example, we're just reconfirming and in some cases getting closer to the mathematical fit that Neuquén had made for the previous data sets. Okay, and here another very important thing. Okay, these N of 1 values that are plotted here, okay, if you want to fit a new chronology function, you must always use the same production function to calculate these N of 1s. So here I'm saying it over and over again, you always have to make sure that you use a production function that's the same when you want to compare your N of 1s, and a production function is only to be used with its corresponding chronology function. Otherwise, you're going to end up having some problems with your output of your data, and then you won't be able to interpret it in a robust way. Okay, so just continuing the calibration, Apollo 11, Apollo 12 are published in Icarus, and then 17 is almost ready to go. 15 is getting there. 14 and 16, Gia is supporting the master's students who have also done the maps. So the maps are basically done, and we're at the manuscript stage for moving forward with updating those. And we just recently published, we supported Yuki Qian in China with his work on making a geologic map of the Chang'e 5 landing site and deriving N=1 values that can be now, they're ready and waiting for sample age analysis. So we can then plug it into the chronology. Okay, so I wanted to come back to this figure again because this question mark just really eloquently expresses what was a problem in 1975 is still actually, until December, a problem for us too, because we did not have samples from known provenance from this entire range of ages from 3.2 to 1 billion years, okay? And so this is then the rationale behind proposing the isochron mission to the P60 basalt unit south of Icarus, south of Aristarchus, and also the Mons Rumker region for the Chang'e 5. Here, what I've done is plot the N=1 values for the 2 units, basalt units, and Chang'e 5 landed on EM4, but the 2 basalt units in the Mons Rumker region. And then I also plotted the N=1 for the P60 unit to show you basically that, okay, based on kind of the variability of all the different chronology function fits, this is where we would expect the sample ages to turn out. So anywhere here between about 1 and 2 billion years. And so I'm really excited to see where this will turn out. Okay. So we're missing information from this middle time. We have samples from one location. And we're also missing information up here at the old end. Okay, we worked on a paper with Ian Garrett-Bethel about whether or not there's a sample of SPA and what this would mean for the late heavy bombardment and the impact rate on the early moon. But we really don't have a sample of SPA that we know for sure is from SPA. And so this is the rationale for a moonrise mission to return samples from SPA so that we know if the chronology function should be steeper here or if it's shallower. If it's steeper, that means that things were really heavy during the early part of the moon. If it's shallower, then there's a lot more time for all of these basins to form in between Imbrium and SPA. And this is another question about Nectaris. Where does it fall? Because Nectaris is one of the marker basins, and depending on where it falls in terms of age, it brackets then a large number of basins in between it and Imbrium. So we also need to gain information about these old units. Okay, and I mentioned just briefly earlier that then you can update chronology functions. And here's the example for Stuart Robbins' function that he updated using his data set that he collected. Again, chronology functions should always be paired with a specific production function. And then, as I mentioned earlier too, Marky had made his own production function using the modeled size frequency distribution of impactors. And then he produced a chronology function that is paired with that production function. And here in his 2009 paper, he compares that with the Neuquén the Neuquén and Evanoff data set, which are the data points and the chronology from Neuquén. Now, one other thing that has been used to update chronology functions is to have a look at the fact that the impact rate on the moon is not isotropic, it's asymmetric because the leading side receives more impacts than the trailing side of the moon. And so the Forêt and Zurich basically corrected the N(1) values for this impact asymmetry and then fit their own suggested chronology function. And so in this 2011 paper, you can find their comparison to the Markey and the Neukom chronology functions. Okay, so we've talked about some of the recent updates and ongoing updates for the actual tool of the Lunar Cratering Chronology and the chronology functions. Now you want to know, well, how do I do it? How do I measure a CSFD and what is it good for? So now I'm going to talk about applying the cratering chronology. And so essentially, I mean, the top line is that you want to use the cratering chronology because you want to know how old a geologic unit on the moon is or on a different planet that hasn't been sampled. Okay, so you're going to go in and you're going to map your homogeneous areas. They need to have minimal slopes. You want to avoid secondary craters. Typically, the count area is not the same as the mapped unit boundary. In this case, we have a very nice clear boundary between the mare infill and the crater. And so here would be a case where the count area is the same as your mapped unit. But for example, here for the ejecta blanket, you would want to go a little bit farther away from the crater rim. You would have mapped your ejecta blanket all the way up to the rim, but your count area might be out here because you want to avoid the steeper slopes close to the rim. Okay, so you're going to measure the diameters of all the primary craters in the area. And here, you know, sometimes from students, I get a question, well, yeah, what about the secondary craters? You know, do I measure them or do I leave them out? Well, if you have a lot of secondary craters in your area, you need to redefine your area because you want to avoid them. So that basically you want to minimize any errors from the geology and from secondary craters before you even derive a CSFD. Okay, so let's say you've successfully measured all of your craters, you plot them up in your cumulative plot here. Then it gets fit with the lunar production function, this red line. Okay, and then you can go over and solve for your N(1). Okay, so now you have a relative age as your N(1) value. Okay, so now we want to have to solve the cratering chronology function for this N(1) that you've measured. And so you go over and solve for the chronology, and then you get an age, and it's called an absolute model age. Okay, so now you know that your mare unit is about 3.1 billion years old that you measured. Okay, there are a lot of things that you kind of have to keep in mind when you're doing this process. And this is a sort of a listing of all the ones that we could think of. I broke them up into two types of factors. You know, there's method-specific factors like how good your image is, the image resolution, the geometry of the illumination, and the count area size, because we're talking about statistics. If your count area size is too small, your statistics get bad because you have fewer craters in there. There's also issues about variability of crater detection and measurement across the practitioners. And then sometimes there's just incorrect fitting of the data sets. So those are all kind of method-specific ones. We've also got geology-specific ones. So this would be specifically that from a geological perspective that you've selected a poor count area, or perhaps you have a count area that you really can't improve at all. For example, the irregular mare patches, they're just very small and there's nothing that you can do about it. So you just have to do as well of a job as you can and be aware of the caveats and discuss that then in the papers. I mentioned that you want to try to avoid slopes. In some cases, you might have an issue where you have endogenic craters that end up in the CSFD. Secondary craters are a major theme here because they, of course, are going to increase the number of craters that you're counting and would then increase the age that you derive if you've included too many of them. Equilibrium is the case where the production of craters reaches a steady state. And this happens when you have older surfaces. The smaller crater diameters reach a steady state where the same number of craters are produced as are destroyed. And when you're in that situation, you can't fit them with the production function anymore. It has a different slope. And so then you can't derive any age information. Then we have things like crater degradation effects that would remove craters from your population, target layering, strength and gravity scaling effects. Smaller craters have different scaling characteristics, and this may lead to some pretty significant apparent age differences. Then for old surfaces, you have a problem with crater non-sparseness, where new craters partially destroy older craters or completely destroy older craters. And there's some recent work that uses a buffered non-sparseness method to help compensate for that. And then I also mentioned the asymmetric impact rate. So I see that based on the time, I'm unfortunately not going to be able to go into detail about any of these, but we can certainly in the questions address a couple of these. And like I said, I'm happy to come back at some point and do another seminar that's more specific about this. So I'm just going to skip this. Okay, so I want to get to like the big questions before we end and have some discussion. And that is, okay, we've counted all these craters. What are we going to do with them? And this is the fruits of labor, or if you're if you've slaved away for hours and counted, like I think Harry counted something like 25,000 craters in SPA, and Mike Zaneni was one of our master's students. He counted tens of thousands of craters. So maybe it's really the grapes of wrath instead of the fruits of labor. But what can we do with all of this data? Well, when we look at the really big picture, we just be able to say that my unit is 3.2 billion years old. We can start looking at a global scale and taking a look at the global development of different geologic processes on the moon. And so this is one of the iconic versions of this view from Harry Hiesinger. And now with Chrissy and Basin added, it's going to be in the New Views of the Moon 2 chapter. And so you can see the distribution of ages of the Mare basalts over time. Okay, and this then is just an eye-opening new way to look at the global distribution of Mare. And you can see then that you know, there are distributions that we find out then are actually related to the thorium compositions and other remote sensing concentrations of composition. Okay, so this type of comparison wouldn't have been possible without using the lunar cratering chronology. And then now that one of our PhD students who just defended about 2 or 3 weeks ago, Jan Hendrik Haskert, had done a lot of work on small basalts on the lunar far side, and he was able then to make a comparison between the distribution of occurrences of Mare on the far side to the near side, and you can see that actually the volcanic activity on the far side was pretty consistent with the near side activity. That's just one highlight from his work. Okay, and then we can expand this to looking at a map of work by Yu et al. That's summarized again in this New Views of the Moon chapter, looking at the ages of wrinkle ridges. And here we can see that there are a lot of older wrinkle ridges in these colder colors, but there's a concentration of wrinkle ridges in Mare Tranquillitatis that are really quite young. And we have actually two students who've been doing theses comparing Serenitatis and Tranquillitatis and trying to get an idea of why is that the case? Why are those two regions slightly different? You can also, for example, look at the distribution of light planes and their ages, and that with the aim towards trying to figure out really what the origin of the light planes is. Are they all originating from a single basin impact? For example, do they all originate from Oriental ejecta or Imbrium ejecta? Or do we have a mingling of material that's basin ejecta from many different basin impacts? And then you can see that here, with little dots, because this is no longer billions of years scale, it's a millions of years scale. We can look at the distribution of ages of lobate scarps across the moon. This is work that was done by Jackie Clark when she did her PhD with us and is currently in revision. And we didn't end up seeing any kind of global trend in the ages of the scarps that she looked at, but that in itself is also an interesting result. And so I look forward, hopefully her paper will come out soon. You can get more details there. Another way, besides just looking at global distributions of ages, that we can leverage all of these counts that we've done is to apply them to setting absolute timescales for geologic maps. And this is just an amazing map that one of our PhD students has finished, and we're working on the manuscript. It's a map of South Pole Aitken Basin, extending from the South Pole also over to Oriental Basin, since Oriental influences this region so greatly. And so she and Misha Ivanov Misha Ivanov started by doing the Apollo Basin region, and Claudia extended it to this area, with Misha doing a bulk of the work in Oriental. And these units are then basically fixed by marker units that have the ages determined for them. So that, I'm sorry, I grabbed the figure that didn't have the absolute time scale on it, but here we can apply an absolute time scale so that we can compare the formation ages of all of the different units within the geologic map. Okay, this also helps in terms of understanding the geologic evolution of the region, because then you can look and see if the map makes sense with how you're interpreting the stratigraphy and how the crater size frequency distribution derived ages are coming out. And so this is a really powerful way of adding additional information using the Lunar Cratering Chronology to geologic maps. For example, break out using ArcGIS. Now we're so flexible with geographic information here that we could break out and look at just the nectarian and pre-nectarian materials that are in the SPA region, or we can just look at specific Imbrium system crater materials, or we can pop out just the plains units. They're both light plains and dark plains or Mare units in here. And so the flexibility of this is a really powerful tool now to get into looking at lunar deep time and really getting the big picture. So the calibration of lunar stratigraphy to the sample ages allows this bigger assessment of the geologic history and evolution. And here I'm showing an updated stratigraphic column for the moon that's presented in Hiesinger and Tanaka. It's geologic time scale. showing, that how it can be actually fixed to absolute time. Okay, and so, the absolute times help us then define the lengths of these different periods, for one thing. But then we can take it a step farther and to steal, to kind of coin another term off of John McPhee. He had Annals of the Former World. Here we have Annals of the Former Earth, because we can now compare the lunar deep time directly with the Earth deep time, with this entire geologic history. And it enables the comparison then of both terrestrial and lunar evolution, because of course they are linked. And the really important part of this is that the moon preserves the early history of the Earth-Moon system, which has been largely erased on the Earth due to water and plate tectonics, and of course, vegetation and things like that. And so the moon is really the history book for the early terrestrial history here. Now, one of the other really important things that has been a focus recently for a lot of different projects, working groups, also for NASA, has been then the correlation between this geologic time and the development of life. And the ability to know what's happened in terms of bombardment in the early Earth-Moon system from the moon then helps to feed into our understanding about how and when life formed on the Earth. And I'd like to point out too something that just from examining these timescales in different ways that I think is just one of the interesting things, and just take some time to reflect on this yourself. But the Copernican period of the moon, we always kind of say, well, that's young craters. Okay, they're young, they have nice rays, and you can see them really well, and they're young. Well, the Copernican period started on the moon actually before multicellular life formed on the Earth. So the Copernican is not really that young, is it? Maybe at some point we'll be able to divide that Copernican period into some smaller, into some smaller periods with looking at the irregular Mare patches and scarp activity that's recent. So I want to end on also showing the stratigraphic columns that he's going to present for Mars, Venus, and Mercury. And you can see Venus is just packed up here on top of Mercury because Venus really doesn't have an old history. Its surface is less than 600 million years old. And then we've got Mercury periods are being developed currently with all of the excellent data coming from that has been analyzed for Messenger. Bepi Colombo is on the way. So hopefully we'll be able to then have more information that we can use to continue to refine where exactly the Calorian, Tolstoyan, pre-Tolstoyan periods happen in terms of absolute time. And then of course for Mars, it's really important to have an idea for the climate evolution across time, and also to try to fix this against our time scale on Earth so that we know approximately when the climate change on Mars happened as a solar system process. And this here, for example, fixing a Martian chronology is the goal, for example, for in situ geochronology missions, and that's kind of the looking forward, is to collect enough samples from Mars that then we could have a Mars chronology system and not always have to rely on the moon. But I hope that I've convinced you during this seminar that the Lunar Cratering Chronology is a pretty amazing tool, and while complex, allows us to have a much broader view of the evolution of the solar system than we would have without it. And so I'll stop there and I would be happy to take questions.
Thank you so much, Carolyn. That was a great talk. I see Patrick McGovern in the chat. Finally, Chrissy, I've been waiting for this for decades.
Yeah. I'm just going to open chat this real quick. Yeah, yeah.
I was just wondering what,
Christian,
why it took,
Christian, oh, sorry, yeah?
Go ahead, Pat.
yeah,
Yeah,
I
go
was
ahead.
wondering why it took so long for Harold and team to do Crisium as opposed to all the other ones.
Yeah, Crisium was unfortunately not very well covered with lunar orbiter data. And so that's why it kept getting pushed off until until now. Harry actually had done Crisium, I don't know, maybe it's early 2010s now, and just unfortunately did not have time to publish it. It's available as an LPSC abstract, but the manuscript to actually publish the Mare counts is sitting on his desk still. But finally, the nice map, adding it to the map, that is going to be available in the New Views of the Moon chapter, hopefully coming out relatively soon.
Okay, thanks.
If you have questions for Carolyn, please type them in the chat or let me know if you'd like to ask them directly. I know it's sometimes a little bit difficult to get a sense for the appreciation, audience appreciation in these virtual talks. I'm sure you're used to that by now, but
Yep, definitely.
if you want to let Carolyn know if you enjoyed the talk, I see Thomas is in the chat mentioning that, but that is very much appreciated here in the audience.
Yeah, and if anybody has a question later or you don't feel comfortable asking here, feel free to send me an email. I'm happy to exchange on email. Then Julie just wrote lovely timeline figures. They are in, I think it's a journal or a book called the Geological Time Scale, which is mostly terrestrial. So definitely go find that and check it out, because it's a really nice chapter.
So Christian asks, since the lunar highlands are so bombarded, how do we know that there aren't a large number of ancient craters that have been buried and are beyond recognition?
Well, you know, there's certainly some craters that probably have been destroyed. But if, for example, you take a look at SPA, it's the largest impact basin on the moon, but we still have evidence for it. And you can trace not the entire rim, but a good part of the rim is traceable. It's visible into topographic data. What we've noticed, and I'm sure other crater, basin scientists have noticed this too, is that the basins are really hard to erase completely. Just because they're so big. It's easier to erase a small crater because they're not as deep, and yeah, it's just a smaller amount of destruction that you have to cause to remove it. And so it's actually a really interesting process, which is something that gets into the differential degradation of craters, that the smaller craters actually do disappear more quickly. Okay, so I see David Kring is asking what are the challenges of determining ages of cryptomare using crater counting. Yeah, I mean, cryptomare is like a mare that then has been covered with material like light plains material, and so then the question is, if you're measuring craters on that surface, what are you measuring? And this is actually one question that that Claudia Purla, she was the one that has done the SPA map. She worked on light plains for her master's thesis with us, and we have a new PhD student who's doing some light plains work. That's really the question. you have to have craters that are going to be big enough that they basically don't see this layer of light plains material that's on top, or just, you know, light ejecta material that's on top. So you have to be very careful not to interpret an age for cryptomare that is determined for very small craters that really just are representing that layer of material. So you would maybe look at craters that are dark halo craters, because you know that that's exposing the cryptomare. And then you would have, I would look and see what the CSFD looks like overall, and see if there's evidence for resurfacing at a younger age where that light material was deposited. But yeah, it's a good question. Okay, then we have a question about reevaluation of late bombardment. Yeah, I mean, this evaluation, reevaluation of late bombardment is still a really hot topic, both from the modeling side as well as from the CSFD measurement side. The work that we did with Ian Garrett Bethel suggested that if the sample that their team suggested was SPA with a 4.26 a billion year radiometric age, if that's really SPA, combining that with the N of 1 value that that Harry had determined for SPA, then it would argue against a sort of a cataclysm and for a monotonic decline of impactors over time. And that's actually consistent with some new modeling that Morbidelli has done. I think 2018 might be his newer paper. He has another one in 2012. So those are also good things to have a look at for more information. But this debate is still, you know, going on. That's why we need a sample of SPA, by the way, that we have known provenance. Okay, so basins only recognizable through GRAIL. Would it be safe to use an inferred diameter and perform crater counts from there? I think, sorry, I'm not thinking of his name at Brown. Andrew, I think, has done some work on doing a size distribution of basins based on gravity data. Yeah, I mean, that you could, I think an inferred diameter, you could try using an inferred diameter, but you would have to be aware that the diameter that's displayed in the GRAIL data might not actually be representative of the full basin diameter where the rim would have been present, because there's often not a real good correlation between the rim and the gravity signature. Okay, and then we have a question. Can we be sure that areas with relatively few craters aren't actually older, but just happen to get a few impacts in areas that seem to have more craters? Yeah, I mean, you're right about being concerned, because the random crater process does not necessarily produce a random, well, I mean, it doesn't necessarily produce a visual distribution that you would recognize as being random, just like for the eye. Because in a random distribution, you can have clusters of craters, or you can have areas that are non-sparse, okay? And so that is a situation where you need to have a large enough count area so that you have a large enough number of craters to give you a good statistical basis for calculating your age. Okay, and then Tom is asking about factors affecting CSFDs. You think that mare resurfacing processes should be added to geology-specific list, or does it fall under target layering? Yeah, that's kind of that's a kind of a target layering item, but yeah, maybe it would be useful just to have added just a geological resurfacing, because there are other things that can cause a resurfacing or a resetting of the craters. Specifically, what Tom is probably referring to is that you can actually measure a kink in your size frequency distribution that then can be traced to a younger lava flow that has covered up an older lava flow. So you see the large craters on the older part, and the small craters have been erased and then are reset and are growing again on the young area. Another process that can happen that I looked at in a 2018 paper is shaking from scarp formation. Scarp formation apparently actually shakes the surface enough that it can reset the small crater population. And that basis is what Jackie Clark used to then generate that globally distributed set of scarp age data.
Fantastic. I think we have maybe time for one more question if anybody has one, but otherwise it's about 4:10, so I think we're going to be closing up the seminar shortly. But thank you so much for this great talk. It was really good. I really appreciate you being here, especially with calling in from in Germany. I know it's quite late there, but really appreciate your talk. So the LPI virtual seminar will continue next week. Our guest next week will be Jessica Sunshine of UMD, and we will be sending out the announcement about that shortly. But, thank you all for coming, and have a great afternoon or evening, wherever you happen to be.
Take care, everybody.
Take care.